I'm Wenxuan from the Robotics Institute at CMU. I'm going to talk about our work on latent action space for offline reinforcement learning. In this work, we propose a simple and effective offline RL method that learns the policy in the latent action space to avoid out-of-distribution actions. It achieves competitive performance on both simulated and real robot experiments. In a common reinforcement learning pipeline, the agent repeatedly collects interactive data and updates the policy. In contrast, offline reinforcement learning studies the problem of learning a policy from a static dataset of transitions without further data collection. This paradigm will be especially important for robotics. Collecting interactive data in the real world is expensive and potentially dangerous. Static datasets allow more flexibility in data collection. We can include human demonstrations, reuse the rollouts from previous experiments, and also share the datasets within the community. In this way, the static datasets will be more likely to be scaled up in size. Although off-policy algorithms use a buffer to save the rollouts, it cannot be directly used for offline RL problems. This is because in Bellman update, out-of-distribution actions will lead to extrapolation error of the Q values. This error will be accumulated and leads to significant overestimation bias that hurts the performance of the policy. To avoid extrapolation error, we need to constrain the policy to select actions within the support of the dataset. As illustrated in this figure, we can only select actions under a green region. On the other hand, the constraint cannot be overly restrictive. The policy should not be affected by the density of the dataset pi_b. In this example, the policy should have the flexibility to choose any action within the green region, even if it deviates from the most probable action of pi_b, or if the shape looks very different. Previous method is either difficult to satisfy the constraint or affected by the density of the dataset. This motivates our method that meets both of the objectives. In our method, we first model the behavior policy using a conditional variational autoencoder, as in previous work. It is trained to reconstruct actions conditioned on states. The decoder creates a mapping from the latent space to the action space. Thus, we propose to learn a policy in the latent action space and then use the pre-trained decoder to output an action in the original action space. In this way, the policy naturally avoids out-of-distribution actions. Also, it can select any action within the latent space, and it will not be affected by the density of the behavior policy. We evaluate our algorithm on a wide range of continuous control tasks, including a real robot experiment and the D4RL dataset. The task for the real robot experiment is to slide along the edge of the cloth as fast as possible without dropping it using a tactile sensor. The static dataset we use is composed of a replay buffer from a previous experiment and 5 episodes of expert rollouts. Here's the final performance of the policy for each method. Our method can move the farthest comparing to the other baselines. Here are the quantitative results. Directly applying TD3 on the offline dataset fails. Both of the offline RL baselines, BCQ and BEAR, do not perform well on this task. Our method outperforms the other baselines and achieves similar performance as the expert. We also evaluate our method on the D4RL benchmark. Here are some of the training curves. Our method can achieve similar or better performance than the other baselines. More results on the D4RL benchmark can be found in the paper. In summary, we propose to learn a policy in a latent action space to naturally avoid out-of-distribution actions in offline reinforcement learning. More information can be found on our website. This work is supported by the following sponsors. Thank you.